Hello again. Today we would like to talk specifically about the spatial and temporal discretization of our groundwater models. Again, this is the main reference. This is not the only reference, but this is the main reference that we use in this video, and also you've seen this in previous videos. Applied Groundwater Modeling, book of Mary Anderson and William Wisner. The pictures, figures, and graphs that you may see, many of them are coming from this book. Okay, before I start talking about the discretization, there is one thing that I want to mention here in this slide. As you know, this is the governing equation that we have, and we developed this governing equation, for example, for all spatial domain of our model. So for each of these cells or nodes, actually, we would like to go and solve this equation. Okay, but in this course, I don't talk about how you can go and numerically write a code and solve this equation. So this is another topic that I teach in another numerical class. But what you need to learn here in this course is that usually, let's say it this way. So you know that actually ModFlow is the main model which can go and solve this equation for us. But these years, recently, so many user-friendly graphical interfaces has been developed, like GMS, Groundwater Vistas, and so on. There are multiple, but these are well-known ones. So these interfaces, what they do, they help the modeler to pre-process the input data, like recharge, I don't know, storage coefficients, and all of these parameters. It's actually, they help us to graphically develop a very effective and efficient system. That in next slide you will see. For example, there are some additional features like interpolation models, which helps us to extend the data. We're going to talk about this. So there are some tools which helps us to pre-process the data and prepare and make our groundwater model. And also there are some very useful tools to, let's say, post-process the outputs. Okay, like again, actually, you will see later that actually once the this equation is solved, you can go and, for example, find or to better visualize the results. Okay, so these two pre and post processes are very useful tools that are hidden in these GUIs. Okay, and GUIs, the heart of the GUIs are the actually the ModFlow. Okay, so but these GUIs, to solve this equation, they can use multiple numerical solvers or numerical approaches. For example, DE4 or direct method, GMG, LMG, PCG, SIP1, and SOR1. So these are just names of different numerical approaches which go and solve this equation for us. Okay, so technically, usually this is not the area of our interest. Usually mathematicians and computer engineers, maybe, they go and develop these solvers for us, and we as a user, we go and select one of these and solve our equation. But each of these solvers has advantages and disadvantages. For example, some of them may converge, some of them may not. Some of them are fast, some of them are slower. For example, if I'm not wrong, for example, now in this year, I think this is the only solver which we can use to use parallel system, parallel computational system to solve our equation. Okay, so for example, there are differences between these, but if you want to know the details, each of these solutions has its own documentation that you can go and Google and find and read more about and learn what are the advantages but disadvantages. But this is the PCG is, I would say, would be the most common solver that we use. But as a modeler, you have to go play and pick these models and play with them and see how they respond, how they converge, and there might be some packages which would work with one solver but not the other one, but it is developing. Okay, so it is progressing. This part is progressing, but you as a modeler, at least you need to learn the name of these solvers. Okay, for example, PCG is one, GMG. So these are the names that at least you have to keep them in your mind. Okay, we have two forms of discretization. Spatial discretization and temporal discretization. What does it mean? Spatial discretization you are pretty much familiar with. For example, if this is my conceptual model, technically that would be 3D, right? I divide this, for example, if I look at this is the plane view, so I divide this. So technically, to solve the governing equation, by solving the governing equation, we mean that, or in other words, the solution of the governing equation is limited to points at the center of these cells. Okay, what I mean, so we want to find hx, hy, xz, and hd. Okay, but to find that, we don't go and find the head here or head here or head here or head here. So we find the head exactly at the center of each cells, and if we need to exactly find a head here, we need to come up with some sort of interpolation or change the mesh sizes and have a smaller sizes. Okay, so these are the spatial discretization that actually we are going to talk about in next slides. But there's another form of discretization, which is temporal discretization. For example, again, we are going to go into the details of this, but for example, our model would start from 2006 to 2010, for example. We can divide these into smaller, let's say, time steps. Okay, so we are going to talk about this and actually how we can do that and what does it mean. But technically, we divide the duration from 2006 to 2010 into small pieces and maybe even way smaller pieces, and go and solve, actually find a head within those time steps. You as a modeler, once you have developed your conceptual model, you need to decide what are your delta x. So for example, if this is my cell, this would be, for example, my delta x, this is my delta y, and also delta z in another axis. Okay, so you as a modeler need to decide what are your delta x, delta y, delta z values. Okay, but how you decide? So usually there are some. So usually what we do, we start by developing a very simple models, and we keep going, and based on the objectives of our models. Okay, so we go and decide what delta x, delta y, delta z suit better to our model. But you need to know that usually, most of the times, if you use more cell size or greater cell size or smaller delta x, delta y, delta z, if your actually cells are smaller, technically you increase your accuracy, but on the other hand, you increase the computational time. Okay, so you need to compromise. I mean, it's a trade-off. So you need to think about this. If you have a computer which is fast enough, or if your model is kind of small and you don't worry about the computational time, so you're welcome to go and use a very fine delta x, delta y, delta z, very fine cells. If your model is, for example, if it is a regional model, if it is it's a very big model, for example, a statewide model, then probably you cannot go and use very small delta x, delta y, because the computational time would be problematic for you. Okay. And note that we're going to talk about the steady state and transient state solution. So sometimes in the transient models, technically you repeat solving the equation so many times based on your delta t's, right? So that's why sometimes it may take days or months to go and solve a groundwater model. But now these years we have a way better computer models, and also we can use a parallel computational approach to increase the speed of calculation. But this is something that actually you as a modeler need to think about and decide, and making decision process would be, usually it is a trial and error process. So you go and play with your delta x, delta y, delta z, and see actually how it works. What I want you to learn in this session is that I want you to learn that there are two discretization philosophy, I would say. The one is the using a structured form, and the other one is the unstructured form, that it is a more advanced and interesting system that you'll see in a few minutes. But the traditional mod flow is based on this structured discretization, and again there are some packages which are designed to help you to create and structured and spatially discretize your system. For example, this is another thing which is within those GUIs, which GUIs that actually helps you to discretize the system. But structured system, which is a traditional system, is a system which each cell, as you can guess, is rectangular. Okay, so it's a cubic system, and the node is sitting at the middle of this box. Okay, so this is a picture that actually you can take a look at. As you see, everything is cubic and in the rectangular form. And also to address these cells, we usually use an IJK notation. It is like the IJ part is like what we had in the Excel row column, and I don't know what is the other one, depth or whatever. So the IJK system, okay? This is actually one advantage of that. It is simple to address these cells. Okay, so this is one advantage of the system. The other advantage is that to calculate the flow rate, which at each face of these cells, technically you need to know how the system is connected to the neighbor cell. Okay, but the connection between these cells are simple because everything is cubic, and technically it is very easy to mathematically define the connection between these cells. Okay, so these are the main advantages, but there are some this system has some disadvantages that you'll see next slide. Let me first talk about and introduce the unstructured, and later on we'll go and compare the structured and unstructured, and then you can see what are the advantages and disadvantages of these using these system. But unstructured system is an advanced and recently developed spatial discretization, which actually the mod flow is known as mod flow USG. This system uses a finite volume instead of using finite difference, which was in the structure and traditional groundwater. It uses finite volume formulation, and it has a very good. It has a very good advantages. Okay, that we are going to talk about later. But before comparing these two models, you need to know that there are multiple ways to develop an unstructured system. So usually they categorize them into 3 groups. The one is the nested unstructured grid, nested grids. Okay, so in the nested grids, as you see, there are some, for example, if there is a well here, we already talked about this, if we are interested to know better what's happening around the well, we need to use smaller systems, or if there is a river or boundary condition that actually we would like to know how the system is responding there. So, but anyway, if there are areas that actually we would like to increase the resolution, we can locally increase the resolution using a nested grids. But as you see here, again, everything is rectangular, even in these areas. Okay, so that's one way. The other one is quad tree. Again, it is pretty similar to this idea, but the discretization is different. So technically, as you go away, so you define, for example, if this is the well, as you go away from the well or whatever, or the point of interest, so the resolution decreases or the cell size increases. So this is one way that we call it quad tree, but the most interesting and useful unstructured grid system is a Voronoi system, that actually, as you see, the cells are not cubic, and they may have different shapes. And actually, if you want to increase the resolution, you can simply go and increase the resolutions locally there. Voronoi structure is a very interesting structure which naturally exists in the system. For example, in the turtles that you see, you see a very similar pattern, or on the dried clade system you see pretty much similar pattern, or and on the skin of the giraffes. And also there are so many interesting examples that actually we see those Voronoi pattern. Okay, so let's talk about the differences. The first difference is that the unstructured models have higher accuracy, and they usually converge better compared with the traditional structured system. But on the other hand, since they have different shapes like this, so defining the connectivity between each node, or addressing these nodes, are a little bit more complex. But there are some approaches that actually we can go and use and mathematically define this connection. I would say this is not, in most cases, it is not a big problem. But technically, you have to have more information, or create more information about your cells. The other difference is that as you see in this picture here, for example, if the dark area is my conceptual model, and if I want to use or create a groundwater model for this dark area, technically I have to create a big cubic system like this. Okay, as you see here, I have to create that big cubic system and put my conceptual model within that box, and then deactivate these cells. Okay, so technically my main model is rectangular. So these cells technically, although they are inactivated, and there are ways to inactivate them, it is not difficult, but they exist in the calculation. They you need to the computer need to assign them in its computational memory. Okay, so this is a big drawback of using unstructured system. As you see that actually I don't know, maybe there are 13% of the cells are I technically don't want them to be in my model, but due to the structured system I had to have them. But so as you see, this is a non-efficient system, but in the if I wanted to use an unstructured system, I don't have to have these extra cells. I can limit my model exactly and very efficiently within the spatial domain of the conceptual model. This is a big difference. Okay. Okay. The third difference is that, for example, here in this is the unstructured system. So usually, if we don't have access to ModFlow USG or the packages which would help us to use an unstructured system, what we have to do is that, for example, if there are things here that actually I want to have more accurate information and results, I have to increase the resolution here. But in the unstructured system, I can go and refine the cell sizes here. But what happens is that if I define extra rows here, as you see, these rows extends into the entire space domain. As you see, for example, I don't want to increase the resolution here or resolution here or resolution here and here. Okay, so this is my area of interest. But in the unstructured system, unfortunately, I cannot do that, and it creates an extra cells that I don't want. So this is another difference. But in unstructured system, for example, if this is my river system, I can use a nested grid system and quadtree system, and also locally increase the resolution here and increase the resolution. But as you see, the Voronoi unstructured system, as you see, if I want to increase the resolution along the river, I can beautifully use smaller cell sizes there. Okay, you see, and also as we discussed in previous slide, I don't have to have a cubic system like what I have in these three examples. I can exactly match my cells and numerical models and create very smooth edges at the border of my conceptual model. Okay. Another big difference here is that essentially in the unstructured models, layers have to be continuous across the entire space domain. What does it mean? For example, as you see here, suppose that I have a sandy aquifer. I have a sandy aquifer here, which extends like this, and actually this is the recharge area of my confined system. So do you remember the so we already talked about this. If this is my for example, if this is the system, the confining aquifer is something like this usually. Okay, so there is a recharge area that actually the water gets into the system and eventually comes into the confined system. Okay, so if I have a system like that, or if I have an outbreak, or if a one layer geological layers pins out like this, usually it is very difficult. There are some ways to do that, but I would say they're usually they are problematic and inefficient. So, but here in the unstructured system, I can beautifully create a system like this. So I can define a layer, as you see this blue layer. So I can define that blue layer starting from here and ends exactly here. The same, you see that actually there is another. So I can discontinue the layer. Okay, but if it was the structured system, I had to extend these layers somehow. I don't know how, but I had to extend these into the end. And usually, if I want to, I would define a very thin layer, but there is a minimum. You cannot go and have a very, very thin layer, but you can go and kind of define a thin layer, or there are some other tricks that you can use, but you don't have that problem using advanced multiflow USG or unstructured system. Okay, you know, you as a groundwater modeler, you have to go and discretize the Z direction of your model. Okay, for example, suppose that I have a groundwater model like this, which has 3 layers. Okay, and we usually use the hydrogeological or geological units information to define these cells. But suppose that actually I'm looking at from the side, and these are my cells. Okay, so as I see, actually I have these on the other sides as well. Okay, and assume that, and actually I have defined a boundary condition here and the boundary condition here, and I have the flow, and assume that actually the groundwater table is something like this. Okay, so what I want to talk about in this session is that there are very slightly differences between the confined and unconfined definitions in the groundwater hydraulics viewpoint and let's say numerically modeling viewpoint. Okay, you'll see that you are familiar with the confined and unconfined definitions, right? But in groundwater, in numerical world, okay, by definition, the confined layer is slightly different. Okay, so but you need to learn and pay attention to in the confined system, and this is exactly what you see in the GUIs, okay, or in the multiflow model. Okay, so the definition of confined and unconfined is different slightly. So the layer is confined if the head of the water is above the top layer of the system. For example, if you look at this cell, the head of water is not above the top of the cell. But if you look at here, the head of water here is above the top of the cell. So in this situation, this is the confined layer, okay? And it is important because if it is confined, then this is the saturated thickness for that cell, okay? Which is already known, right? So we know the size of this, and computer know the cell size, and if it has the head, and you can go and derive the gradient here and multiply it by k and so on to find the flux here, okay? But if the head is below the top of the layer, like what you see here, this is considered as unconfined, and the system has to go and find the saturated thickness, and based upon that finds the flux information or the flow information, internal flow information, okay? So that is the main difference. But you know that if you have, for example, if you have a pump here, so for example, there's a pump here in this cell. If you start pumping, you know that what happens. So you would go and change the, so let me erase this one. In this case, you can go and change the groundwater head profile into this. And if it is a transient pumping, so it pumps, stops, and it pumps, it stops, stops, pumps, it stops, like this. So then this would fluctuate. Okay, so in this case, there is another type of layers which we call it convertible layers. Okay, so the convertible feature allows the modeler, or allows the model to go and check if the head is on top of that. It considers that actually it is a confined layer, or if it is not, it goes as considered as unconfined. So technically it goes and check the head with the top of each cell, okay? And why it is important, you know that, so we already talked about the in the governing equation for the confined system is different from the unconfined system, right? So the one difference that we see here is the saturated thickness of the cell. Okay, so that is one difference. The other difference is that you remember that actually we had different storativity parameters, specific storage and SY. So in the unconfined system we have to use SY, and in the confined system we use the specific storage coefficient. So there are differences here. So the governing equation is different, and also the way you define or calculate the internal, we call it internal flow, is different, which is a function of the saturated thickness. Okay, so that's why usually people in the GUIs or in the models, they go and check the cell to be as convertible, but it is not always the case. There are cases that actually we although know that, for example, in this case, so it is good that actually I talk about that. There are some cases and situations that you see that although the modeler knows that this is an unconfined layer, okay, although it knows, but due to the convergence problem, usually the convergence problem is an issue here, we force the computer to consider this as a confined system. Okay, so technically we have to do this because we see that actually the model does not converge, or it cannot takes care of this unconfined system for some reasons. Okay, so what I'm saying is that there are some situations that we may force a model to consider an unconfined layer a confined layer, and it is possible. Actually, it's simply you can go and define and force your model to say that, for example, consider the first layer always as a confined system. Okay, so this is an approximation actually. Okay, for example, this is the governing equation of a confined system. As you see here, there are some parameters like kx, ky, kz, and s storage coefficients, and also the sink and sources information that technically it doesn't matter, it is a structure or unstructured system. In both of them, if this is the cell, the k value or the storage coefficient value is assigned and considered within this cube, okay, within the entire space of each cube. So the k and actually these parameters or let's say material parameters or properties can be categorized into hydraulic conductivity, as you see here, kx, ky, z for each cell, and again if it was a different unstructured system, again it doesn't matter, everything is assigned to the entire space. So the hydraulic conductivity is one, the other one is the storativity information, and actually effective porosity is something that actually we need to know. Usually this is a property that actually we need to add, but it is more important once we do and solve the contaminant transport models. But these are three informations that it doesn't matter if it is structure or unstructured, so it is assigned to the entire volume of the cell. As we already talked, once I was teaching developing the conceptual model, you know that if this is my conceptual model, I know that usually the system is not, I have heterogeneity in my system, right? So the nature is usually, most of the time, it's heterogeneous. Okay, and since this system is discretized into multiple cells, I can kind of match or define heterogeneity by assigning different k values or s values for each cell. Okay, so but usually if you would like, usually we use the field data, for example, based on some field investigation. I go and find the hydraulic conductivity or porosity information in this point, and 1 point here and 1 point here. For example, the K here is 10 meter per day. Here it is 5 meter per day, and here it is 8 meter per day. Okay, so to take care of this and to extend these data and assign a proper values for the other remained cells, there are three main groundwater techniques. Okay, the one is the zonation technique, which is a traditional and very common approach, and numerically it is more stable and fast. But the other model is the interpolation system. The other approach is the interpolation. Technically, we use an interpolation calculation and assign a proper values to these cells. And the other one is the hybrid approach, which is nothing but the combination of these two. In some areas we use zonation, in some areas we use interpolation. So this is all called as a hybrid approach. So these are two examples of using zonation techniques. For example, there is one field measurement here, one here, and one here. Okay, and based on some mathematical techniques, so technically, I think you're familiar. I mean, if you connect these lines together, and if you go and actually, I don't know, find the middle of those lines and draw a perpendicular line, you can go and define the zones which are closer to each point. Okay, so for example here, this point is closer to this one, that's why I assign 100 to this. But this cell is closer, the closest point is this, and that's why I assign 60. Okay, so this is the philosophy of this model, and I can go and define zones myself. Okay, and using techniques like this, also I can go and use the geological maps like what I see here, and I force the system to say that, for example, for these cells, if the cells are here, for these cells use a specific number. Okay, but the idea here in the zonation technique is that the value is constant within the entire zone. Okay, so for example here, all of these numbers are 50. Okay, so the number in each zone is constant. Okay, so this is a very common and actually very stable. For example, this is a very stable approach if we want to calibrate our models. Okay, but there are much more complex approaches that you'll see in next slide. As you can see here, there are two interpolation techniques. Usually, I mean, we can divide them into two groups of deterministic and geostatistical approach. For example, inverse distance and polynomial fitting is a deterministic approach, and geostatistical Kriging approach, which is very common, and we usually use this system to interpolate the information. So herein, if we have a number here, number here, number here, number here, technically, as you see, we don't define any zone. So the values, as you see, the values of these cells changes based upon as you go further from these. For example, this is 100, this is, I don't know, for example, 95, this is 80. So as you see, based on the colors, you can go and calculate the system. So this is one way. This is an inverse distance interpolation, and this is a linear interpolation. As you see that actually this is another approach that you see the contours here. So in this system, you don't have a zone which has one constant. Okay, so technically you create, I don't know, for example, whatever it is, 1000 Ks or S values using these fours. Okay, but within with zonation, you may have way less K values, like 10 K values. Okay, so because you assign a constant value to the entire zone. So the hybrid approach is nothing but the combination of the zonation and interpolation at some points. Excuse me. At some points, for example, we use zonation and constant value, and in some areas we use an interpolation techniques. But if you remember, once I said that there are these GUIs that we use to create or set up our mod flow models, they have these techniques or approaches within, which helps the user using very user-friendly graphical interface, which helps you to create or spatially discretize your system and assign the material properties to each cells, okay, using interpolation or zonation techniques. So that's why actually now these years creating or setting up a mod flow is way easier than what it was years ago, which everything was based on text files. So in previous slides, we talked about how we can spatially discretize our space domain. And herein I want to talk a little bit about how we can discretize, temporally discretize our model. As you already have learned, we have two types of solutions, right? The steady state solution and transient state solution. Okay, so we know that this is simpler, and in the next slide we'll talk more about when and why we need to use the steady state. But this is a decision that usually a modeler needs to make. Okay, so once he was developing your and you'll see that actually there are some approaches to decide if you as a modeler need a steady state model or a transient model. Okay, we are going to talk a little bit about that, but you know that the transient is in the transient state mathematically the right hand side is 0. And it means that because mathematically the head does not change with time. Okay, so it is 0. So the right hand side is 0, and it is easier to go and solve this problem compared to the transient situation where the right hand side is not 0. What I want to emphasize here is that I want you to note that you should not underestimate the steady-state models. That's true that steady-state model is a simplified form of what we really see in the nature, which is always in the transient situation. So the groundwater is always fluctuating based upon the recharge information. So it is very rare that we find a groundwater system which is truly in the steady state condition. But steady state models can create sufficient amount of information or good enough or accurate enough groundwater flow information for us, which everything depends on the model objectives. Okay, so for example, the steady-state model can estimate the average groundwater flow patterns and flow rates. Okay, so for example, if you want to find the annual flow rate, or how the groundwater changes annually, or what is the average flow direction, it is from north to west, or whatever, you can go and just simply use a steady state model. Or for example, you can create an average annual leakage for losing the stream. So as you see that actually you can create a very useful average information. Okay, or regional water table gradients or flow directions influenced by long-term pumping or drought. Okay, but the key is that you have to in the steady state system, you need to pay attention that you create an average information usually within the long period of time, for example for 10 years, or it depends to your model, or 2 years. Okay, if you see that your system or hydrological forces, for example the pumps that you have, or the river stage that you have, or the lakes, if you see that the hydrological forces don't change dramatically within a long period of time, you can assume that the system has effectively reached its steady state, and you can just use a steady state model, which is much more faster and usually more stable, and also it is way easier to calibrate. Okay, so but these were the things that you need to know how you may decide to have a steady state or transient state. But there is a very important things that I'm going to talk about in next slides. You'll see that in the transient solutions, as you know that actually the main difference between the steady state and transient state solution is that in the steady state solution you don't have the storage, you don't need to have a storage coefficient information. This is a big advantage, so you don't need this, and also you don't need an initial condition. Okay, so the initial condition is not necessary once you're solving for a steady state. Okay, but for transient state, you have to define S sub S, and also you have to define an initial condition. For example, if your model wants to start from 2005 to 2015, you need to go and find the groundwater, so you need to go and get some potentiometric information and kind of come up with the initial condition information. Okay, but as I'm going to talk more in next slides, practically it is difficult to go and define a proper initial condition, and the initial condition, which is in the first steps of calculation, are very important, because the model is way sensitive to the initial condition, and it needs to converge real quick within the small delta t. So if your initial condition is too off, you'll see that actually your model will quickly crash. Okay, so it is very difficult, and usually it is difficult and tricky to find a proper initial condition, because you need to have an initial condition which is kind of stable and kind of match with your boundary conditions. Okay, so that's why usually it is much more efficient and it is much more practical. We start the transient solution with an steady state condition. What does it mean? It means that if, for example, if this is my time domain, for example, it is day 0, day 1, day 2, day 3, day 4. Okay? So, for example, my delta t here is 1 day. Okay? So there are two ways to start model from time 0. One way is that I define an initial condition manually, let's say, using the potentiometric information. I go and assign a probable values here. So this is not efficient. Usually the model crashes, but The other way is that first for delta t, for t0, I go and solve for a steady state solution for that small delta t. Whatever the boundary conditions are in that situation, whatever they are, I fix them and I go and solve a steady state governing equation just for delta t. So I assume that at time 0 the system is within the steady state conditions, because that's a more stable condition which better matches with my boundary conditions. Okay, so technically my boundary condition has created that initial condition. Okay, so after that I use that solution as my initial condition, and I keep going and solve for the transit. So technically I myself go and create the initial condition using the steady state solution. So this is the most, it is very important, and as you will see in the future, you'll see that it is much more better way to solve a transient or define an initial condition. So if you remember in previous videos, we talked about how we need to make our decision to have a 1D, 2D, or 3D models. You remember? Now we started to talk about, okay, so now we need to have a steady state model or transient state models, okay? If I want to summarize what we've talked about, answering this question depends on the modeling objectives and time frame for modeling. For example, as I said, actually, if you want to have an average information, for example, for multiple years, then actually this is something that we can consider, and also the budget or amount of time and money we have to model and finish this project. So these are the things that we need to consider. But the rule of thumb is that even if it is necessary to have a transient model, we better start with a simple model and create a steady state model. Okay, so based on that, we can go and learn more and feel better our groundwater model. So we usually start with a steady state model, but you know that the groundwater systems are never at steady state. That's fine, but steady state models, so these are the advantages actually. The steady state models are simpler to create, it is easier to execute, and post-processing is even easier, for example, for calibration, because you don't have to, so you have one run of one shot. Okay, so technically you can simply go and calibrate this model, but and also steady state models need only a single set of calibration data, and it means that actually if you want to calibrate your data, you go and have, for example, if you have a calibration target, it is just one calibration target. So that calibration target, it's not does not change with time. It means that actually it is simpler, and also you don't in the steady state models you don't have to have the storage coefficient, which is technically it is very difficult to find and calculate. Okay, and also it is independent of the having initial conditions. So these are the advantages, and based on these you can go and decide whether if you want to have a steady state or transient model. So those were the advantages of steady state models, but there are some cases that actually we can't use the steady state model. For example, if we want to know how groundwater would fluctuate based on daily pumping rate changes, or based on the flood, or based on the rainfall events. So if you're looking at the smaller durations, technically we have to use a transient model. Okay, we already talked about the initial condition, and we said that actually most of the times we want to start the model. So for example, suppose that actually this is my time 0, this is my time 1, this is time 2, this is time 3. So these are my time steps. So we said that usually it is better to first go and solve for the steady-state solution of T0 with its own boundary conditions at T0, and then start solving for transient solution. As you see, for example, this is a dialog box of GMS, which allows you to go by checking this box. Technically, you force the system to go and solve this equation in steady-state solution for this, and then technically define the initial condition. Okay, and once you have the initial condition, it goes and solve for the other ones. And we say that actually it is usually practical to do this. Usually the model does not converge with the manually input initial condition, but not necessarily. I mean, there are cases that actually it works, but I want just to, if you want to learn more about the philosophy and why we do this, excuse me, you can go and read this paper. It's a very interesting and classic paper in applied groundwater modeling, and you see that why it is better to do this. But usually the noise modelers usually want to have their own initial condition, use those, but it is not practical, which is explained here. Not always. I mean, usually it is not practical. Okay, now let's talk about the time discretization. If you look at the transient solution here, there's a delta t here that actually we need to define. This is the delta t of the modflow solver actually. Okay, so we have two types of time discretization. One time discretization explains how the boundary conditions and the source and sinks terms fluctuate. Okay, it represents these two processes, and there is another time discretization, which is nothing but actually this the numerical model solver delta t. Okay, this picture is I would say it is the best picture to explain this. So if you look at this, it assumes that the pumping rate is constant, and suddenly it goes up and gets increased to a certain level. Okay, so how we discretize the time here, we define a stress period. So the stress period actually is associated with the boundary condition and sink and source terms, okay, within the system. So we define a stress period, and by definition, the transient stresses, for example, pumping rates, river stage, etc., can only change at the beginning of each stress period. So this is a trick. This is the confusing part. So it means that at the beginning of each stress periods, this is the only time when, for example, the pumping rate can change. Okay, so as you see, it is constant within the stress period, and again at the beginning of the next stress period, it can go up and it is constant like this. Okay, so as you see that usually for pumpings we have this pattern, it is not problematic. But if this is the stage, for example, the river stage, which fluctuates way smoothly like this, to represent this, we have to have a smaller stress period. So technically you have a system like this. Okay, so that's the stress period. But delta T, the numerical discretization, the delta T for the numerical solver is usually smaller than the stress periods. For example, if this stress period is 10 days, each stress period can be divided into smaller delta T, for example, 1 day. Okay, so this is called time steps, and this is called the stress period. The stress period is associated with the boundary condition and sources, and only at the beginning of each stress period the head would change technically. And but delta T, which we see here, is actually the time steps. And you don't have to have a constant stress periods and also constant delta T. As you see, you can play with and define them different. And again, the GUIs help us to pre-process and come up with the good. And usually if we make a mistake, for example, in some of the stress periods, a window pops up and actually it explains that actually, for example, there would be an issue in the stress periods, and go and fix it, or it automatically goes and fix the problem. So this is another advantage of using GUIs. Okay, taking care of the time discretization of a model is not easy. This is something that you need to consider, and usually it takes time. But it used to be way more confusing and difficult before these GUIs that we have. Again, I mean, the GUIs helps us to pre-process, and sometimes, for example, if you've made a mistake in defining the stress periods, so a window pops up and says that, well, that there's a problem there, go and double check, or it provides some solution and says that actually, do you want me to go and fix the problem or not? So these are some things which are put within the GUIs, which significantly help the land water modelers these days. But these two pictures are again, this is a confusing concept, but I hope that you will understand the issues here. Okay, so as we said, within each stress periods, only at the beginning of each stress periods you can go and change the value of W or the value of the boundary conditions. For example, if this is my W, recharge, and if this is how the recharge or rainfall happens, and these are my stress periods. So the model first goes and read the value of recharge at the beginning of the stress period, and I put it there, for example. Okay, so and actually this was extended here, but for the second time steps, it goes and read the head here, the recharge value there, and it put it there. So within the entire stress period, the value was constant. Then at the beginning of this stress period, it jumps up, goes there. Okay, for the second one, again, it goes and read this number, and it is constant until then, but it suddenly drops. But as you see here, we missed the signal because it is within this big stress period. So technically, I had to switch and put this stress period here to be able to go and read this. Okay, so I have to play with my stress periods and match it with my W term. So this is something that I need to be careful and I need to think about it. But usually if I use a constant time scale for all my W terms and all my boundary conditions. At least these two are consistent, and I can match these with a proper delta t and actually come up with a good pattern. But this is something that you need to be careful. So traditionally the mod flow was like this, but GUIs recently have had an interpolation tool where it works like this. Again, at the beginning of a stress period, it goes and reads the value. At the end of at the beginning of the next stress period, it goes and read, but now it goes and interpolate, but linearly interpolates and create values within the stress period. So in other words, in this system, the value of the W or boundary condition is not changing. It is not constant within the stress periods, but it linearly changes. Okay. For example, suppose that this is the boundary condition of mine, and actually it fluctuates like this. Then I had to go and play with these and come up with a proper delta t. So, and you know that my delta t's are here. So it means that for each delta t, its model goes and changes the boundary condition information. It is not constant like this within the entire delta t, but this is another way to go and take care of the time discretization. But remember, it is not easy. Okay, so it usually takes time, and you need to spend time and go and come up with proper time discretization. But these GUIs these years help the modelers a lot. This is another practical example. Here, as you see, for example, I think this is the pumping rate information, and as you see, for example, you can divide your or define your stress periods like this, and you go and calculate the average value of your fluctuation. For example, here the average value is 6.9, this is 7.26, and actually what happens here, what you're doing, you are simplifying the system to this system. For example, something like this. So these are the things that you need to be careful with. So delta t itself is an issue that you need to think about and work on it. So I want to stop here, and I hope that you have learned useful things, specifically about the spatial and temporal discretization and structured and unstructured systems, and also the differences between the steady state and transient state models. Thank you.